Adelaide is a city in South Australia and it's one heck of a complicated place geologically speaking. The rocks here are ancient and have undergone several tectonic events that have led to a complex and somewhat confusing array of geological features in present day. Beneath the sediments of the Murray Basin is a truly ancient volcanic arc that roared to life at some point 800 million years ago. This volcanic arc was formed by subduction processes and it released violent explosive eruptions with pyroclastic flows that covered the then barren land beneath vast amounts of volcanic material. But along with this, the area also experienced another tectonic event. A rift zone formed to the west of the arc 830 million years ago, and the two may have occurred simultaneously. This rift is known as the Adelaide Fault Belt, and it's a geosyncline. A geosyncline is a large-scale depression in the Earth's crust that's filled with thick sequences of sedimentary and volcanic rocks. This geosyncline rifted at least 5 times in its history, and the reason it formed is thought to be associated with the breakup of the supercontinent known as Rodinia. This rift basin was later to form during the Delamerian orogeny approximately 514 to 500 million years ago, when the region experienced significant tectonic compression due to a subduction event in Western Victoria, which led to the folding, faulting and metamorphism of the sedimentary and volcanic rocks in the geosyncline. This orogeny uplifted the region from a flat basin to towering mountain peaks, and it transformed the region into a complex fold belt, as well as depositing vast mineral wealth in the process. If you live in Adelaide, you are literally a short drive to the goldfields. But this video is about the largely hidden Nackara Volcanic Arc. This arc is now being investigated with the suspicion that it holds vast untapped mineral wealth in the form of copper and gold porphyritic deposits, along with a host of other metals and rare earth elements. Porphyry intrusions occur primarily at the end stages of volcanism as the magmatic system begins to die down. Small-scale mining was conducted in very specific areas around this arc in the early days of the gold rush, but it wasn't known to be a volcanic arc back then. It's only when we view the region under magnetics that we can get an idea of just how vast this arc stretches, and boy is it a big one. When this arc roared to life, the erosion of it filled the Adelaide geosyncline with volcanic deposits along with sedimentary deposits that dominate it. Outcrops of this arc are rare to say the least. The porphyry intrusions of the Nackara Volcanic Arc are thought to host gold and copper in economical amounts, meaning it could be rich enough to mine on a large scale, and exploration and drilling are still underway to deduce the richest areas of the arc. Due to its age, the exact identity of the oceanic plate involved in the subduction process leading to the formation of the Nackara Volcanic Arc is not precisely known, but can be referred to as the Proto-Pacific Oceanic Plate, which subducted from the west to the east beneath the stable continental craton known as the Gawler Craton, which is truly ancient in its age, with its formation dating all the way back to 4 billion years ago. As a side note, if you're enjoying this video, please click the like button to help YouTube recommend it to others. We also have a Patreon if you'd like to support the channel, only if you have the means of course, and you can find that both in the description and in the pinned comment down below. If you've watched the previous video that I've made on the Stavely Volcanic Arc, linked down below, you'd know that its birth was during the Cambrian 520 million years ago. This coincides with the birth of the Delamerian orogeny in the Adelaide geosyncline, which squashed, bended and buckled the sediments and volcanic material, forming a vast and towering mountain range in the process. The Stavely Volcanic Arc owes its existence to the subduction event that took place when the Paleo-Pacific Ocean subducted beneath the Indo-Australian tectonic plate. And as mentioned before, the effects of this subduction event extended beyond Victoria, and it reignited the ancient fault lines within the Adelaide geosyncline, with recent depositions of granites and mafic to intermediate rocks like diorite and gabbro occurring amongst several other intrusive rock types. It's not only gold and copper that's being explored. Deposits of kaolin and rare earth elements are linked to this arc. The tectonic collision that formed the Stavely Volcanic Arc in Victoria are directly related to causing the Delamerian orogeny. Australia is truly an ancient landscape, and many volcanic arcs have formed the vast history of tectonic collisions and mountain building the continent has undergone. We'll continue to explore more of these in future episodes. So until then, thanks for watching. The Gympie goldfields, located in southeast Queensland in Australia, are part of a broader geological structure known as the New England Origin. The Gympie goldfields are the result of a series of geological processes that took place over hundreds of millions of years. From the initial deposition of marine sediments in a geosyncline to the complex tectonic interactions involving subduction, volcanic activity and mountain building. Each step played a crucial role in concentrating gold into economically significant deposits. The hydrothermal systems, driven by the heat of rising magma, deposited gold in quartz veins, creating the rich mesothermal gold deposits that have made Gympie a notable gold mining region. Gympie is one of the closest goldfields to Brisbane. The Gympie goldfields were discovered in 1867. The amount of gold extracted from the Gympie goldfields is quite substantial. Over its mining history, the goldfield produced more than 3.5 million ounces of gold. The discovery of gold by James Nash in 1867 triggered a gold rush. The initial years saw a rapid influx of miners and the establishment of a thriving mining town. During this period, gold was primarily extracted from alluvial deposits, which is gold that is found in riverbeds and streams. Nash found gold in the alluvial deposits of the Mary River and its tributaries. While many nuggets were found in the Gympie goldfields, the exact record of the largest nuggets can be sparse due to the historical nature of the gold rush. However, some notable nuggets include the Curtis nugget, which is one of the most famous gold nuggets found in Gympie. This nugget weighed approximately 975 ounces, which is 27.7 kilograms, and it was discovered in 1868. It is one of the largest nuggets ever found in Queensland. Throughout the late 19th century, numerous other large nuggets were discovered in the region. Reports from the time mention several nuggets weighing over 100 ounces, which is 2.8 kilograms. Even today, gold prospectors in Gympie occasionally find gold nuggets using modern metal detectors. While the major gold rush days are over, the region's history and remaining gold deposits continue to attract hobbyists and small-scale miners. Alluvial gold is typically found as nuggets and flakes that have been eroded from the primary gold-bearing rock and transported by water. The ease of finding gold in riverbeds attracted thousands of prospectors to the area, leading to a gold rush. As the alluvial gold became scarcer, miners began to extract gold from deeper underground veins. The development of underground mining techniques allowed for the extraction of gold from quartz reefs. This period saw significant gold production, with numerous mines operating in the area. By the early 20th century, the easily accessible gold deposits were largely depleted, leading to a decline in mining activity. However, technological advancements and improved mining techniques allowed for intermittent mining activities throughout the 20th century. These activities focused on extracting gold from lower-grade ores and remnants of older workings. In recent years, there has been renewed interest in the Gympie goldfields, with modern exploration and mining companies investigating the potential for new gold deposits. Advances in mining technology and exploration techniques have the potential to uncover additional resources in the region. But how did the goldfields here form? Well, this all somewhat started with the New England origin. I say somewhat for reasons that will become clear shortly. The New England origin was initially shaped by the deposition of thick marine sequences during the Devonian and Carboniferous periods, about 419 to 299 million years ago. These sequences were deposited in a geosyncline, a large-scale depression in the Earth's crust that collected sediments. The Gympie region's rocks tell a fascinating story of how the Earth's plates have moved and interacted over millions of years. Imagine the Earth's crust as a giant puzzle made of pieces called tectonic plates. Sometimes these plates collide. When an oceanic plate, which is denser and thinner, hits a continental plate which is thicker and less dense, the oceanic plate gets pushed underneath in a process called subduction. As the oceanic plate moves under the continental plate, it scrapes off sediments, loose materials like sand, mud, and small rocks, and pieces of oceanic crust. These scraped off materials get piled and squeezed against the edge of the continental plate, forming a mix of rocks known as an accretionary wedge. The rocks in this accretionary wedge are not just piled up neatly, they are twisted, folded, and broken because of the immense pressure and movements during subduction. This makes them look very complex and jumbled, like a crumpled piece of paper. Some of these rocks are cleaved, which means they have split into thin layers due to intense pressure. Melange structures are areas where different types of rocks are mixed together chaotically, resembling a rocky stew. To put it simply, the Gympie region's geological formation can be visualised as a conveyor belt where the oceanic plate moves underneath the continental plate, scraping off loose material and rocks from the ocean floor. These materials get squished and piled up at the edge of the continental plate, much like how snow piles up in front of a snowplow. Due to the constant movement and immense pressure, these piled up materials get twisted and folded in many different ways. Imagine trying to push and squeeze a stack of papers. They wouldn't stay flat, but would crumple and fold. In this chaotic mix, you get a variety of rocks all jumbled together. Some rocks get split into layers, while others are mixed together like ingredients in a rocky salad. This process of subduction and the resulting formation of complex rock structures are crucial in understanding how gold deposits and other minerals come to be in regions like Gympie. The intense geological activity creates conditions that can concentrate valuable minerals, making them accessible for mining. Whilst associated with the New England origin, the Gympie province has its own designation. It has been interpreted as including components of an evolving volcanic arc that collided with the eastern margin of the Australian continent in the early to middle Triassic. This is why I said it's somewhat related to the New England origin, as the Gympie region actually developed outside of continental Australia, as a standalone volcanic arc in the open ocean. It was only during the Hunter-Bowen orogeny that it became accreted to mainland Australia. It's likely that the New England origin produced the magma needed to form the arc, but it was a separate entity that formed some distance away from Australia at its beginning stages. During the early to middle Paleozoic era, around 541 to 298 million years ago, subduction of the Paleo-Pacific Oceanic plate beneath the Australian continent led to the formation of volcanic arcs and the emplacement of granitic batholiths. This subduction was a key driver of the geological processes that formed the gold deposits in the region. The rising magmas carried gold and other minerals, which were deposited in the crust as the magmas cooled and crystallized. The Gympie region still exhibits geological features characteristic of ancient volcanic arc systems. The presence of volcanic rocks such as basalts and andesites indicates past volcanic activity associated with the volcanic arc. As the oceanic plate subducted beneath the continental plate, it generated significant heat and pressure. This caused partial melting of the subducted plate and the overlying mantle wedge, creating magma. The magma, being buoyant, rose through the Earth's crust, leading to volcanic activity at the surface. This volcanic activity formed a chain of volcanoes, similar to the modern-day Pacific Ring of Fire. The rising magma also intruded into the crust, forming large bodies of igneous rocks known as batholiths. These igneous intrusions played a crucial role in the mineralization processes that eventually led to the formation of gold deposits in the region. A major tectonic event, the Hunter-Bowen orogeny, occurred during the late Permian to early Triassic periods, about 260 to 250 million years ago. This event was characterized by intense folding, faulting, and metamorphism, significantly impacting the structure and mineralization of the Gympie goldfields, and it led to the accretion of it to mainland Australia. There are major faults in Gympie, which acted as conduits for gold-bearing fluids to rise and deposit auriferous quartz into the fractured Permian age sedimentary bedrock. The emplacement of granitic batholiths during the Siluro-Devonian period, approximately 425 to 400 million years ago, initiated hydrothermal systems. These systems involved the circulation of hot mineral-rich fluids through fractures and faults in the crust, leading to the deposition of gold in quartz veins and lodes. The hydrothermal fluids were primarily modified meteoric and magmatic fluids, which leached gold from the surrounding rocks and concentrated it into economically viable deposits. The Gympie goldfields are characterized by mesothermal quartz gold base metal sulfide deposits. These deposits formed at moderate temperatures of between 230 to 350 degrees Celsius and depths typically associated with mountain building events and hydrothermal fluid activity. The gold deposits in Gympie share similarities with other significant goldfields, such as Charter Towers and the Mother Lode deposits of California. To summarise, the formation of the Gympie goldfields involves subduction and subsequent accretion of oceanic materials onto the continental margin. Emplacement of granitic batholiths and associated volcanic activity provided heat and fluids for hydrothermal systems. The circulation of mineral-rich fluids through fractures and faults led to gold deposition in quartz veins. Multiple phases of tectonic activity, including the Hunter-Bowen orogeny, contributed to the structural deformation and mineralization of the region. As time goes on, I intend to cover many other goldfields across Australia and the world and explain the geological processes that led to their formation. I hope you found this as interesting as I do, and as always, thanks for watching. Volcanic arcs are the byproduct of subduction zones around the world. They host violent explosive volcanic eruptions. But along with this, they also deposit vast mineral wealth into the fractured bedrock, with many volcanic arcs containing significant quantities of gold, copper, silver, lead, and other metals. The reason volcanic arcs form is due to the subducting plate. When an oceanic plate collides and descends beneath a continental plate, water is introduced into the mantle in two ways: by the subducting slab dragging oceanic water down with it, and by the release of water from water-saturated rocks when they reach a specific depth, where the heat and pressure force them to undergo metamorphosis. When water is introduced into the mantle, it lowers the melting point and induces partial melt as a result. Minerals become sequestered and concentrated. They are sweated out, so to speak, from the subducting slab, and the magma and fluids that are released begin to travel upwards due to buoyancy, utilizing the faults and fractures that subduction inevitably creates to ascend where they can become deposited into the bedrock. This is one of the few ways that volcanic arcs deposit minerals into the land. In northern Queensland, an ancient volcanic arc that formed 298 million years ago during the early Permian exists in the northern part of the Bowen Basin. These volcanics were formed during a subduction event, and they outcrop in various areas. We have a high degree of mineralization in some of these areas with copper, silver, and gold occurrences. Other areas, however, are completely devoid of mineralization. On geological maps, the Lizzie Creek volcanic group is represented by a light blue color. Its formation began when the oceanic Paleo-Pacific tectonic plates subducted beneath the continental Indo-Australian plate, giving birth to volcanoes and major earthquakes. These volcanoes were tremendously explosive in their magnitude, with the release of rhyolite and rhyodacite being pronounced. And we have the later formation of a back arc basin in an area where the land was stretched. This is known as the Bowen Basin in present day. This basin deformed a Lizzie Creek volcanic arc in certain areas, and we have other intermingling volcanics that joined the Lizzie Creek in erupting during the early Permian, and it overlaid it in certain parts, such as the Mount Toussaint volcanics and a Strathbogie trachyte. We also have a group called the Mount Wickham rhyolite on the westernmost border of the arc, where the aforementioned later deformation occurred. It appears as though the stretching of the land occurred in the later part of the Permian, after this volcanic arc had existed for over 40 million years, spewing out explosive and effusive eruptions. What's really cool is under magnetics we can see massive dikes or veins that were emplaced by hydrothermal waters and by magmatic processes. Look at the linear lines that exist so abundantly throughout the region on magnetics. It's possible that these dikes or veins might contain high mineralization in areas and yield an abundance of gold, silver, copper, and other commodities. The red lines that you see on the geological map represent them, and they are numerous and quite widespread in places. Right alongside the Lizzie Creek volcanic arc are numerous major intrusive rocks like the Thunderbolt granite. This would have been the fuel source for the volcanoes in the Lizzie Creek complex, and they have been uplifted to the surface. In present day, the mineralization that occurred in the Lizzie Creek volcanic arc occurs most abundantly in the Mount Carlton area. It's only now that we're really beginning to drill into the earth to see if any significant copper or gold deposits exist. Significant is the key word here. There are former prospects that uncovered gold, silver, and copper in the region, but they have been small scale and the yields haven't been great enough for small scale miners. This is typical of volcanically emplaced gold, which, as opposed to orogenic gold, doesn't contain the high yields one might expect or hope to see. But volcanic gold is normally concentrated in certain areas, due to a process known as magmatic differentiation. Magmatic differentiation occurs as magma rises through the Earth's crust. As it does, different minerals crystallize out of the magma at different temperatures. The result is a concentration of valuable minerals like gold, copper, and silver in certain places. This can lead to extremely high yields if the right place is drilled that contains a deposit that was emplaced by magmatic differentiation. The result is a bounty of gold or other metals. Open pit mines are often used to extract these minerals. The Lizzie Creek Volcanic Arc is one of many examples of these kinds of volcanic remnants. Ancient volcanic arcs are scattered all over Australia, speaking to the many different tectonic events the country has undergone throughout time. So this is the story of a once mighty volcanic arc that eventually died off and left behind the remnants and riches from the time when it roared to life, to the point where the magma finally cooled. Thanks for watching. There's a fascinating and incredibly rich mineral belt in New South Wales known as the Macquarie Arc. This geological feature contains an enormous amount of gold, copper, and trace amounts of silver among other economically significant minerals. The discovery of its origin is a narrative of immense geological investigation that involved professionals from multiple fields teaming together to finally discover how the Macquarie Arc was formed. What it uncovered is a truly incredible story. For over a century, the Macquarie Arc has puzzled geologists. How did it form and how did it become so mineral enriched? It's only in recent decades, thanks to advances in geological research and modern exploration techniques, that the answers to these questions have become clearer. The Macquarie Arc is among the top 5 gold and copper porphyry deposits ever discovered on Earth. For the past 15 years, the Cadia mine, which opened in 1997, has ranked either first or second as Australia's most profitable mine. It's produced about 50 million ounces of gold and 1.1 million tonnes of copper since it opened. The Macquarie Arc is fundamentally different from the orogenic gold deposits that enriched Australia during episodes of mountain building and tectonic collision. Its origin lies in volcanic activity, specifically as a volcanic arc formed in a subduction zone. This ancient volcanic arc was not initially part of Australia. It formed in the Paleo-Pacific Ocean, separate from the continent. Over time, through tectonic processes, the volcanic arc was accreted to the Australian landmass, becoming part of the continent long after its formation. The story of the Macquarie Arc begins with volcanic activity that commenced during the Ordovician period, which spans from around 485 to 443 million years ago. It began with the subduction of the Paleo-Pacific Ocean beneath an oceanic region roughly 500 kilometers east of the continental land of Gondwana. I will clarify how we know this soon. So this was an oceanic to oceanic collision that occurred. As is usual with subduction zones, after the collision occurred, volcanic activity soon followed as the descending plate carried water towards the mantle. As the slab is forced deeper into the mantle under high pressure and temperature, the trapped water is released into the overlying mantle wedge. This introduction of water into the mantle lowers the melting point of the surrounding mantle rock. As a result, the mantle rock begins to partially melt, generating magma. This magma, being less dense than the surrounding solid mantle, rises towards the Earth's surface, eventually leading to volcanic activity. In an oceanic to oceanic subduction zone, the rising magma can produce volcanic islands, forming a volcanic arc above the subduction zone. Early stage volcanic activity in subduction-related arcs is typically effusive, with explosive eruptions becoming more common as the magma evolves and increases in silica content. And this is exactly what happened in the Macquarie Arc. The early volcanic eruptions produced pillow basalts, which formed when basaltic lava erupted underwater, producing pillow-like shapes as it rapidly cooled and solidified beneath the waves. Pillow lavas are distinctive, bulbous formations that only form when lava erupts underwater, where the surrounding water cools and solidifies the outer surface of the lava quickly, causing it to be shaped into pillow-like structures. The presence of pillow lavas in the Macquarie Arc confirms that its volcanic activity began under the sea. The Macquarie Arc can be divided into distinct phases of volcanism, each characterised by unique geological features and processes. Geologists have identified at least 4 major phases of volcanic activity in the region, with each phase marking significant changes in both the physical landscape and the geochemical properties of the volcanic materials. So phase 1 began with volcanic eruptions occurring on the sea floor, where it gradually built up volcanic cones beneath the ocean. In phase 2, these volcanoes would break through the waves of the Paleo-Pacific Ocean, forming island arcs. Eruptions slowly built up a string of volcanic islands as there was a transition from effusive lava flows to more explosive volcanism. This phase was accompanied by significant sedimentary deposition, as the volcanic islands eroded over time, primarily due to the abrasion caused by ocean waves, leading to substantial volcaniclastic sedimentary deposits. These eroded volcanic sediment deposits, consisting of sand and boulders that had been worn down from the volcanic ash and lava, would flow down the flank of the conical volcanoes, gradually working to build up the seafloor, allowing it to transition from a deep environment to a shallower one. And this marked deposit of volcanic sediment is important, because as the ocean floor around the volcanoes built up and became shallower, life began to flourish and some of the Earth's first coral reefs sprang into existence. This is where paleontologists come into the picture. They played a crucial role in piecing together the geological history of the Macquarie Arc by studying the fossilised remains of marine animals preserved in the limestone strata. that formed as the volcanic arc emerged through the waves of the ancient Pacific Ocean. The limestone contains some of the earliest corals, trilobites, and mollusks, such as nautiloids and gastropods, which not only helped scientists date the rocks, but also provided valuable insights into the marine ecosystems that once thrived in the area. By identifying these fossils, paleontologists were able to reconstruct the environmental conditions that existed at the time, such as the depth of the water. Brachiopods, for example, offered clues to the depth of the ancient seas, as different species are known to inhabit shallow versus deep water environments. The presence of these fossils and the conditions in which they are found allow researchers to determine not only the age of the geological layers, but also the changing environmental conditions. But fossils also provided a clue into something we've yet to discuss: the massive sea of sandstone that surrounded the arc. This baffled geologists studying the Macquarie Arc because sandstone typically forms in shallow marine or terrestrial environments, unlike the deep marine setting where a volcanic arc would normally develop, which typically hosts vast deposits of mudstone or shale. This unusual association raised questions about how a volcanic arc, expected to form far from continental sediment sources, came to be bordered by such an extensive sedimentary layer of sandstone. The puzzle of the sandstone's origin and age began to unravel with the discovery of conodont fossils within the sandstone layers. Conodonts are an extinct group of jawless vertebrates, best known for their hard mineralized tooth-like structures called conodont elements, which were located in their oral cavity and were used to process food. Conodont elements are crucial to further understanding the Macquarie Arc, as it is the only part of the animal that was fossilized after death. When these animals died, the fossilized conodont elements became deposited on the vast sea of sandstone that stretched from the Macquarie Arc up to Gondwana. These fossils were dated, and the dating of it revealed that both the sandstone and the arc are the same age. This revelation led to the understanding that whilst the Macquarie Arc wasn't present on the continental area of Gondwana, it wasn't far away from the land either. Rivers on Gondwana were eroding rocks on land and were carrying sand into the deep ocean that lay to the east of Australia. This proves that mainland Gondwana wasn't far away from the arc. So we have a sea of sandstone separating the arc from Gondwana, and shallow limestone that formed around the volcanic islands as they eroded and created shallower marine environments. This allowed for the development of coral reefs and the deposition of limestone in these shallow warm waters. Today's video is sponsored by private internet access. Here's something a lot of people don't realise. When you browse the internet without a VPN, your activity is like an open book. Internet service providers can track every site you visit, everything you search, and even how long you stay on each page. Using the internet without private internet access is like mining for gold without securing your claim. Anyone can swoop in and take what you've worked for. Your data is valuable, and without a VPN, it's at risk. But with private internet access, your data is protected. Without a VPN, your connection is especially vulnerable on public Wi-Fi networks, like at airports, cafes, or hotels, where hackers can easily intercept your data. Their no-logs policy has been proven multiple times in court, so you can trust your privacy is safe. Private internet access creates an encrypted tunnel, locking your information away with military-grade encryption, and it's not just about security. Streaming services like Netflix, Disney Plus, and Amazon Prime restrict certain shows based on where you are. With private internet access, you can change your IP address to one of 91 countries or all 50 US states, unlocking content that's otherwise unavailable in your region. Private internet access works on all major platforms: Windows, Mac OS, Android, iOS, and more. And one subscription covers unlimited devices, so you can protect everything with one account. Plus, signing up is risk-free. You get 83% off plus an extra 4 months for free, which is only a couple of dollars a month. And if it's not right for you, there is a 30-day money-back guarantee and 24/7 customer support. So click the link in the description to sign up or go to piavpn.com/OzGeology. And thanks again to Private Internet Access for sponsoring today's video. This is where we discuss the geochemical compositions of the arc, which allowed us to understand the evolution of it. Geochemistry is fascinating. It allows us to understand the differences in tectonic settings and source rocks that lead to distinct magma compositions. In subduction zones like the Macquarie Arc, ancient altered oceanic crust subducts beneath another plate. This process releases water into the mantle, which helps the mantle to melt and introduces new elements into the magma, giving it a subduction zone chemical fingerprint. Water brings with it important elements like rubidium, potassium, and barium, which are key indicators of the subduction process. As the mantle melts and the magma rises, it carries the unique chemical signature of a subduction zone. By analysing the cooled rock, geochemists can determine its origin. One of the most revealing clues comes from trace elements, rare but crucial components that provide insight into the magma's source. Scientists can measure trace elements such as lead, strontium and neodymium at incredibly precise levels, down to parts per billion. Through this method, it was discovered that the Macquarie Arc, including its high calc alkaline rocks, was almost certainly formed in an intraoceanic arc setting, above a subduction zone but far from any continental crust. The trace element analysis revealed no geochemical evidence of continental crust involvement, confirming that Gondwana, the continental landmass, remained far to the west during the formation of the arc. However, scientists also noticed a change over time. By analysing more rocks, they found that the chemical composition of the ancient lavas shifted. Slotting these variations into the fossil timeline allowed them to divide the arc's history into 4 distinct phases, revealing the complex evolution of the Macquarie Arc. This brings us to Phase 3. At this point, subduction had occurred for around 30 million years. It was marked by pronounced changes in geochemical composition, likely due to the influx of seamounts within the subducting plate. These seamounts clogged the system and created added compression in the volcanic system, trapping magma deep within the crust and altering its mineral composition. The eruptions of the arc likely became more explosive compared to the earlier phases. This phase produced andesitic to dacitic magma, which is more viscous than the basaltic magma of earlier phases. As the magma became more silica-rich, it also trapped more gases, leading to the buildup of pressure that resulted in highly explosive eruptions. These eruptions likely produced pyroclastic flows, ash falls, and other typical features of explosive volcanic activity, marking a clear transition from the more effusive volcanism of the earlier phases to a more volatile-rich volcanic environment. In the final phase of the Macquarie Arc, just before the subduction system came to an end, a transformative period of volcanism occurred that would ultimately shape the Arc's rich mineral wealth. This last stage saw a shift in magma composition, possibly triggered by renewed subduction, which introduced fresh arc lavas and created ideal conditions for the formation of the Arc's valuable mineral deposits, releasing vast amounts of copper and gold. One of the most significant outcomes of the volcanic activity within the Macquarie Arc is the formation of porphyry mineral deposits, particularly in regions like the Cadia Valley. These deposits formed through magmatic hydrothermal processes, where large volumes of molten material from the Earth's crust and mantle rose to fill vast bathylitic magma chambers situated 6 to 10 kilometers below the surface. As this molten material convected and circulated within these chambers, it facilitated the extraction of metals, including copper and gold, from the magma. The exsolution of hydrothermal fluids followed, transporting these metals upward along porphyry intrusions to locations about a kilometre below the surface. Here, the fracturing of rocks allowed for the deposition of valuable minerals, often associated with quartz veins. The relationship between gold and copper became particularly evident, with gold often found in association with chalcopyrite and occasionally appearing as free gold within quartz veins linked to bornite. Other minerals, such as magnetite and pyrite, also played significant roles in the mineralization processes within the porphyry deposits. The geological history of the Macquarie Arc takes a distinctive turn with its collision with Gondwana. The collision was unlike typical subduction scenarios, as the arc and the continent were situated on the same tectonic plate, separated by a wide ocean floor filled with sandstone. As subduction ceased, the site where the subduction zone occurred ultimately became fused together, but the Pacific plate continued its westward movement, ultimately leading to the inevitable collision between the Macquarie Arc and Gondwana. The ocean floor, comprised of several kilometres of sandstone, became trapped and wedged between the two landmasses. All the layers on the seafloor were deformed and compressed against Gondwana's eastern margin, crushing and uplifting the island chain and surrounding sandstone. As this seafloor rose to form new land, the Macquarie Arc was broken up and divided into several distinct belts. These belts are now mined in present day, and contain substantial amounts of gold and copper. Today, the sandstone, limestone, and the Macquarie Arc stand as uplifted geological features, offering crucial insights into the ancient tectonic, volcanic, and marine processes that shape the region, with the rich mineral deposits of the Arc continuing to be of economic and scientific importance. So, this is the story of the Macquarie Arc and its mineral deposits. I hope you found this to be as fascinating as I did. And as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.